prepared a nice graphical summary of this chapter, and I want you to go through this summary before solving questions from this chapter. This summary, 2-slide summary, it will cover each and every single thing from this chapter, and you will observe that this is the same summary as we did in chapter 8. It's not different from that one. Now, to summarize chapter 9, you will be asked to test hypothesis about 2 parameters. One of them is the population mean. The other one is population proportion. There are no cases under population proportion, sample size big, sample size small, sigma known, unknown, no cases. If the question you recognize is about population proportion, simply you will use a, this is wrong, I will change, I think there is a problem in this one. You will use a z. That z is p hat minus p naught divided by p naught into 1 minus p naught over, let me change it here, and then I will revise it later. This is z equals p hat minus p naught over p naught into 1 minus p naught over n square root. You will simply use a z test. If the question is about mean, then you have 2 cases. You will look inside the question whether the question is giving you the population standard deviation or the question is giving you the sample standard deviation. It is tricky. I accept it. It is tricky to identify from the question statement if the given standard deviation is sample standard deviation or population standard deviation. The best way to judge is check the whole sentence. Is it about the data or is it about the distribution? If the sentence is about distribution, distribution is population. If the sentence is about data or it is giving you the mean and standard deviation in the same sentence, that means it's the sample mean and the sample standard deviation. Then under the mean case, you have 2 cases. If the question is about mean when sigma is known, you will use a z test. If the question is about mean and sigma is unknown, you will use a t test. But when we look at the t table, we see only a few numbers of degrees of freedom are available in the t table. Let me show you the t table. When we look at the t table, here is a t table. You see that the degrees of freedom are available up to 100. You see there? After 100, there are few degrees of freedom. They are available in gaps. But after 250, nothing is available, right? So if you get a sample size such that n minus 1 is not available in the t table, then you are in trouble. And to take you out of that trouble, we have this case, which says that if sample size is large. Now, what is the quantification for large? Degree of freedom is not available. That's the quantification of large. Degree of freedom is not available in the t table. If you are unable to find the exact value from the t table, you will get it the approximate from the z table. So that's case number 3. This is it. Then after choosing which test you will fit, next question is how to find the p-value or how to decide about rejecting H0 or failing to reject H0. That will be helped by this slide. In this slide, you can clearly see that the decision rule, the p-value expression, they don't depend upon what parameter you are testing. They don't depend upon whether you are testing mu or you're testing p or whatever. They depend upon the sign of H1. They all depend upon the sign of H1, the most important sign, the sign of H1. If the sign of H1 is not equal to, and you are doing a z test, then the critical region will be 2-sided and the p-value will be 2-sided. If the sign of H1 is less than, and you are running a z test, then the critical region will be less than and p-value will also be less than. If the sign of H1 is greater than, then the rejection region will be greater than and the p-value will also be greater than. And for the last 2 cases, greater or less, we did not talk about the one-sided, upper-sided or lower-sided confidence intervals in chapter 8. So you will not be asked questions about testing hypotheses using confidence intervals. But we did discuss the 2-sided confidence interval for mu and also for p in chapter 8. So we might ask you a question about testing a 2-sided hypothesis using a two-sided confidence interval from chapter 8. Summary in terms of words. What is the definition of hypothesis testing? It's a statistical framework to checking if the claims about population parameter are true or not. We begin with null and alternative hypothesis, H0 and H1. And after formulating H0, H1, we choose a level of significance. What if it is not available? We assume 5%. Then we compute the test statistic. It depends upon what is the parameter. If you are testing P, the test statistic will be what? The last one, Z. If you are testing mu, the test statistic will be either Z or P, Z or T, depending upon if sigma is known or unknown. After computing the test statistic, you will go back to the p-value expression or rejection region, and you will make decision based on either critical value or p-value or confidence interval approach, and that's it. Now I will go back to the example that we were doing in the previous class related to this case. What is this case? Testing about mu when sigma is unknown. So let us read part 4 of this question. Part 4 of this question says that the sodium content of 20, what is 20? What is this 20? N. 20 boxes was determined. The data gives sample mean of 129 and sample standard deviation of 0.88. Nowhere in the question you are given sigma. Can you support the claim that, what is the claim? This is mu, mean sodium content is what? This is the statement of the question. What is the opposite? So the one with equal sign becomes H0. The one without equal sign becomes H1. Now look at the whole situation. What is the parameter that you want to test the hypothesis about, P or mu? Mu. Is sigma known or unknown? Unknown. Is the sample size small or large? Large means more than 250, and the degree of freedom is not available in the T table. Small, so go for the T. So in this case, T is x bar minus mu naught divided by S over root of N. We found it in the last class. It was minus 1.2705, I guess. Is it? Yeah. Minus 1.2705. Just plugging in the values of x bar, mu naught, and everything. Now the question is asking us to use which approach? P-value approach. I will go to that table from the p-value expression. What is the sign of H1? What is the sign of H1? Less than, greater than, or not equal? So the p-value will be 2 times probability that T19 is greater than T0 absolute. P-value is also two-sided. You will get the probability from one side and multiply it by 2. Why? Because T distribution is symmetric distribution. So we can just take one probability and multiply it by 2. What does this become? 2 times probability T19 more than 1.2705. Now go to the T table and look for the probability T19 more than 1.2705. Okay, here is T19. What is the probability of T19 more than 1.2705? Try to find 1.2705. Is it there? Will it be there? Never be there. But it is between. The value is between this, and the corresponding upper tail probability. This is, remember, this is upper tail probability. So the corresponding upper tail probability is between 0.1 and 0.25. So the table tells us that the probability of T19 more than 1.2705 is between 0.1 and 0.25. Is this p-value? Is this p-value? No, it is not. This is p-value, which is 2 times that. So I need to, throughout, multiply the whole equation by 2. When I do that, I have 0.2 less than 2 times probability of T19 more than 1.2705 less than, and this is p-value. Now this is p-value. So your p-value is between 0.2 and 0.5. What would be your decision? You assume alpha to be 0.05. Is this p-value less than alpha? Whatever it is between 0.2 and 0.5. Is it less than alpha? This p-value is between 0.2 to 0.5. Is not less than alpha. Whatever it is not less than 0.05. So what will you do? We fail to reject H0. When you fail to reject H0, you say that mean is in the neighborhood of 130. You will not say that we accept H0. You will conclude that mean is close to 130, or you will say mean is not different from 130. So answer the question. Can you support the claim that the mean sodium content of this brand is different from 130? No, it is not different from 130. It is in the neighborhood of 130 somewhere. Any question? Few difficult scenarios can be created in this type of questions. Let me tell you what are those scenarios. You might have a question where the p-value is probability of, let's say, T19 more than minus 1.7. More than minus 1.7. The t-table is giving you more than, but the t-table is not giving you the probabilities corresponding to negative values. T-table is only available for the positive side. Here is a t distribution. There is a 0 here. There is minus 1.7 here, and there is plus 1.7 here. And you are interested in more than minus 1.7. You are interested in this area. But t is not giving you this area. What will you do? You can get into this situation. Again, that is using what? Using the symmetry. Look here. We are saying that area above minus 1.7 is the same as area below. Why is it not changing color? Let me use this color. Is the same as area below 1.7. But when you use the symmetry, you will get into this situation. Probability of T19 less than 1.7. Now the value has become positive, but the same sign has changed. Less than probability is not available in the t-table. Now what? Now use the complement rule. Yes. Now use the complement rule. What is the probability of T19 less than 17? This is 1 minus probability of T19 more than 1.7. Correct? Now go to the table. The table will give you this. Probability of T19 more than 1.7. Just for the practice, let me know if you are able to identify this value, T19 more than 1.7. What is that probability? Between what and what? And between 0.05 and 0.1. It's between these two values. Because 1.7 is between these two values. So I will just write what I saw from the table. That probability of t more than 1.7 is between 0.05 and 0.1. So I will simply write what I saw from the table. From the table, I observed that probability of T19 more than 1.7. This is between 0.05 and 0.1. Is this p-value? No. Here is the expression for p-value. You have to manipulate this. Sometimes you'll have to multiply it by 2. Sometimes you'll have to take the complement of this one. Sometimes you have to multiply with minus and so on. So to convert it to p-value, what is the first thing you need to do? Multiply by minus. When you multiply by minus, what happens to the inequality? The inequality reverses, correct? Then add 1 throughout. What happens when you add 1 throughout? Now what is this? Now this is p-value. So you can say that the p-value is between this number and this number, which is between 0.9 and 0.95. What will be the decision based on this kind of p-value, large p-value? Is this less than alpha? No, so you will fail to reject H0. But that's a different story. But you can get into a situation where you at the same time face two problems. Number one, value of t is negative, which is not available in the table. Number two, you are required to find less than probability, whereas the table gives you greater than probability. So to get rid of both of these problems, if you are into a problem that the value is negative, use the symmetry. When you use the symmetry, you have to change the sign of the value and the inequality at the same time. According to the symmetry, probability of TV less than A is equal to probability of TV greater than minus A. This is the use of symmetry. Then after using symmetry, if you still think that the inequality is giving you trouble, use the complement rule to make it greater than. But the bottom line is two things. Number one, T table is available in the greater than form, and T table is available only for the positive side. So you have to manipulate your p-value expression in such a way that your p-value expression is number one, only for the positive value, number two, for the greater than sign. Clear? Let's move to the last part. Yes. Yes, you can get. Not equal to, you will get it something like it is more than 0.99, not exactly equal to 1. Highly supporting H0. Except no, you cannot. Still you cannot. But you will never get 1. You will get 0.99999. Highly in favor of H0. Because the value of t will never be exactly infinity. As the value of t gets closer to, never be close to equal to 0. If it is close to 0, then the p-value will be close to 1. Let's solve the last question. What does the last question say? That solve this same question, two-sided H1, using the confidence interval approach now. You already took the confidence interval in chapter 8. Construct the confidence interval. Let us construct the confidence interval for this question and see if 130 is contained in the interval or not. So again, in this question, the question is asking us to test that mu is equal to 130 against mu is not equal to 130. You will construct the confidence interval, which is x bar plus minus t alpha by 2 with v degrees of freedom s over square root of n. This will be 129.75 plus minus the value of T. What is the value of T? 0.025, 19 degrees of freedom. Why I took 0.025? Because alpha is not mentioned. I assumed it 5%, and because it's a two-sided hypothesis, I divided it by 2. So T 0.025 with 19 degrees of freedom. Can you see it on the screen? What is it? 2.093. So from the table, I got this one 2.093. I will plug it in 2.093 calculators. S is 0.88 over square root of n, which is 20.
But we assume that it's 0.5 because it's 95%.
Because it is 95%.
100.
We did not assume. We took what was given in the question. I was wrong. 100. This is upper, is it?
No.
Lower. Upper. Change it to plus.
.16.
Now the question, does 130 belong to this interval? So you fail to reject H0. Same decision. And conclude what? Same conclusion. Conclude what? That the mean sodium content is not different from 130. It is in the neighborhood of 130. Not significantly different from 130. Last topic of this chapter, hypothesis testing about proportion, P. What is different? Look, nothing is different. Only the test statistic, which will be given to you in the formula sheet. What's different will be given to you in the formula sheet. Only this is the thing which will be given to you in the formula sheet. Only the test statistic. Let me show you the formula sheet for once. Here is the formula sheet. And see, it's given next to the confidence interval. The Z statistic is given, the T statistic is given, but the third Z is not given when sample size is large. You need to understand that it's not a third case. It's a limitation of the T table. When the critical value or P value is not available in the T table, you use Z as an approximation, but only use it when sample size is large. So you will just take this statistic and call it Z if the sample size is large. And here is the third one given. Can you see it for the proportion? All three of them, they are given in the formula sheet. And again, look at the decision rules. Do they depend upon whether you are testing mu or proportion? No, they are the same expressions. They only depend upon the sign of H1. The rejection regions depend upon the sign of H1. The p-value expressions depend upon the sign of H1. Everything depends upon the sign of H1. Regardless whether you are testing mu or you are testing proportion or whatever. Let us move directly into a question. The only trick here is to identify if the question is about mean or proportion. Look at the question. The advertised claim for the batteries of cell phones is set at 48 hours. So the company is claiming that our batteries, they last for 48 hours. You can run the phone for 2 days without recharging it. They did a study. They took a sample of how many phones? 500, and they observed that 15 of them, they stopped, the battery got drained before 48 hours. Then they ask you a question. What is the question? Do these experimental results support the claim? What is the claim? Now I will highlight the claim that the percentage of the batteries that fail before 48 hours is less than what percent? 10%. So I will just read the statement and write the statement in terms of P or mu. Is it about P or mu? Is it the proportion of something or the mean of something? Proportion, percentage or proportion. And the statement is that P is less than. What is the opposite of this statement? Which one contains equal sign? You see, nothing new. Nothing new. The whole chapter is the same story. Which one contains equal sign? Go to the formula sheet and look for the test statistic. It is P hat minus P naught, 1 minus P naught over N whole square root. What is P hat from the data? What is the data saying? What was the proportion of batteries that failed before 48 hours in your sample? 15 over 500. So P hat is 0.03 minus what is P naught? It is the value that you are testing in H naught. What is the value you are testing in H naught? 10%, 0.1 over 0.1 into 1 minus 0.1 over what is the sample size? 5. One of the common mistakes I see is that the students, instead of putting 0.1 here, they put 0.03 here. Instead of P naught in the denominator, they put P hat in the denominator. This is one of the common mistakes we see. Calculator. Check if it is minus. If my memory is correct, I was making slides last night. If I remember it correctly, it is minus 5.22. Can someone find a mistake in this slide? In my writing, I wrote something wrong. No, in the solution, I wrote something wrong. What? No, the answer is okay. Up to 2 decimal, it should be okay.
Yes.
It's okay, right?
Yeah.
I wrote something wrong. What is wrong? What? No. There is not much that I wrote. There is something wrong in I wrote only 3 lines. Where is something wrong? No, I haven't written the conclusion yet. It's written in the blue color with the pen. It's not. H1 is correct. The hat is correct. 0.03. 15 over 500 is correct.
It is not T.
It is not T. It is T. Okay, what is the approach they are asking us to use? Critical value. What is the sign of H1? Less than. So the rejection region will be reject H naught if the computed value of Z is less than minus Z alpha. Go to the table and look for Z alpha. What is alpha? Is it given in the question? No, what will you assume? 0.05. So Z 0.05, when you go to the Z table, it will be between 1.64 and 1.65. You can take 1.64, you can take 1.65. I will take in the middle of 1.64 and 65 because it's, I think, almost in the middle. So you will reject H naught if your computed value of Z is less than minus 1.645. Is it less than minus 1.645? Minus 5.22 is what you got. Is it less than minus 1.645? So what you do? You reject H0 and conclude what? The claim is true. The claim was H1. You conclude that the claim was true. The proportion is actually less than 10%. Is it consistent with the data? You are trying to check that the proportion is less than 10%, and the data told you that the proportion is actually 3%. Is 3% actually less than 10%? Consistent with the data. Logically, right? What if the sample was something theoretical? What if the sample P had, it was instead of 15, it was 45 divided by 500? What if that was the case? It would be 0.09. Is 0.09 less than 10%? But in that case, if you compute the z value, which is 0.09 minus 0.1 over 0.1, 1 minus 0.1, calculator, 500 square root, the z value would come out to be minus 1 point something, is it? Or 0 point something. Minus 0.74. Is it less than minus 1.645? Go for the decision. Is it minus 0.74 is not less than minus 1.645? So you fail to reject in this case. And you conclude that P is more than equal to 0.1. P hat was 0.09. But the decision is that it is not less than 10%. Why did this happen? Because you are in the neighborhood of 10%. H naught includes equal also. So according to your decision, 0.09 is very close to 10%. So you went with this hypothesis that it's either close to 10% or more than 10%. It is not significantly less than 10%. 3% was significantly less than 3%. So you were confident that the distance is too big. So you went with H1. Here, you gave some margin of error. 0.09 is in the neighborhood of 10%. So you don't have enough evidence to say that it is significantly less than 10%. So you will say either it is in the neighborhood of 10% or it is more than. Of course, it is not more than 10%, but it is in the neighborhood of 10%. So this time you went with the H0 because you're not very confident about going with H1. You don't have enough evidence to go with the H1. A very little evidence you got. Very little evidence.
Because alpha?
No, it's not because of alpha, because you are in the neighborhood of H0.
We choose alpha.
No, maybe you'll have to choose alpha to be 30% to reject H0 in this case. Question 2, same question, but this time it is forcing you to use p-value approach. So I will use the same value of z. I got, what was the value of z? I got minus 5.22. H0 was what? P more than equal to 0.1. H1 was P less than 0.1. What is the sign of H1? Less than. So P value will be probability of Z less than minus 5.22. Can someone tell me this probability without going to the table? Just look at this graph. Majority of the Z distribution is between minus 4 and plus 4, almost 100%. Outside this is almost 0. So less than minus 5.22, minus 5.22 is here. So less than that will be almost 0. Because p-value is 0, what will you do? When p-value is small, less than alpha, what do? You will reject H0. The same decision. You will reject H0 and you will conclude that P is less than 10%, which is actually less than 10%. It was 3% from the sample. There was enough evidence to say it is less than 10%. Okay, now I will not solve in detail. You know how to get the p-value from Z and T. I will just construct H0, H1 from the question and leave it up to you to do the details. Read the question and let me know what will be H0, what will be H1. I will highlight what is the question claiming. First, don't call it H0. First, just write the statement. Don't call it H0 yet. First, write down the claim in terms of statement. What is the claim in terms of statement? P equals 0.1. Now write the opposite. P does not equal 0.1. Now this becomes H0. This becomes H1. And you find the value of Z. Then from the last slide, you see what is the expression for critical region, get the critical value, make decision, and so on. This is the same question asking you to test the same thing using which approach? P-value approach. This is the same question asking you to test the same hypothesis using which approach? Using which approach? Using the confidence interval approach. So you will construct the confidence interval from chapter 8 knowledge. From chapter 8 knowledge, you will construct the confidence interval using this formula. This formula is given to you in the formula sheet. P hat is 3%. Z alpha by 2, 1.96. And this will be equal to what? And the upper is 0. How do I know 0.045? It is not because I solved it yesterday. It is because I know that it's metric around 0.03. The middle is 0.03 P hat. Does 0.1 belong to the interval? What will be the decision? So you reject H0 and conclude what? This was your H0. This was your H1. What will you conclude? The claim, what was the claim? Yeah, the claim is wrong. Or you can say that the proportion of batteries that fall run out before 48 hours is not 10%. Either it is significantly less than 10% or it is significantly more than 10%. You will not comment if it is less or more. Just it is not close to 10%. It's significantly different from 10%. Because the question only asked you if to check if it differs from 10%, you will comment only that if it does differ from 10%. Yes. We're not assuming that the process is normally distributed. We are using central limit theorem here from chapter 7, and we are saying that the distribution is approximately normally distributed. This is called an approximate 95% confidence interval. You remember? Yes. So the hypothesis test is also approximate.
So
For P, it's all approximate.
it's the architect.
Yeah. But the exact version is available. We do not teach it in this course, but the exact version from binomial distribution is available. Any other questions? Again, before solving any questions, I want you to go through the last 3 slides of this chapter. I will correct this slide and post the corrected one again. Last 3 slides contain 2 pictures. One picture that gives you a map of choosing the correct test statistic, and the second table gives you, once you choose the correct test statistic, the second one tells you how to write down the expression for p-value or the rejection region expression. So go through these 2 slides, then read the summary of this one. We have not solved a single question related to this one, which we will do in the practice. For computing alpha and computing beta, we haven't solved a single question in the examples. We will do that when we solve old exams and all that. We only know what is the expression for alpha and what is the expression for beta. For expression for alpha, it is the probability of rejecting H naught when H naught is true. Beta is the probability of failing to reject H naught when it is not true. So this is all we know so far. I will use these expressions, and I will use my knowledge of chapter 2 to solve the probability expressions and get the final answers of alpha and beta in the real questions. Next class, I will bring 8 to 10 questions from old exams again, and we will try to solve them. And the class after, we will start chapter 11, which is regression.